Okay, so continuing on the topic of characteristics of a wave, we've so far addressed the wavelength, the amplitude, the crest, and the trough. So now I want to pick up with two characteristics that are associated with time that are inversely proportional to each other. And we've addressed both of these previously. So we have the period of the wave, and inversely related to the period is going to be the frequency. Now, we addressed the period when we were dealing with circular motion, and in circular motion, the period had represented the time for one complete cycle. Well, the same is going to be true in the context of waves. So the period can be defined as the length of time for one complete wave cycle. Okay. And we measure the length of time for one complete wave cycle in seconds. Period is represented by the variable capital T. Okay. So if I were to give you a wave structure like this and say, sorry, that's not a great periodic wave, which, by the way, I'll define that in a second. Okay, let's just pretend that this was really even. Okay, so let's say I gave you this wave and these were uniform. And let's say I told you that this occurred in 4 seconds total. Well, the period of this wave would not be 4 seconds because we have 2 cycles here. We have 1 lambda and then another 2 lambda. So the period, or the time for one complete wave cycle here, t, would be equal to 4 seconds over 2 cycles. In other words, 2 seconds per cycle. Okay, so that would be the period of the particular waveform that I show. Now, inversely proportional to the period is going to be the frequency. And the frequency is represented as the number of cycles per second. And again, this is inversely proportional. Remember, this symbol means proportional to the period. So if you know the period, you can set up the following formula. Well, the frequency will be equal to 1 over the period. In other words, we just solved for the period, 2 seconds for 1 cycle. So what would the frequency be here? Well, the frequency is going to be equal to 1 over 2 seconds. In other words, 0.5. But what is our unit for frequency? Well, technically it's seconds to the negative 1, right? So you could say seconds to the negative 1 as your unit. Or, more commonly used, is the unit called hertz. Okay, hertz. That is our unit of frequency, and hertz is the same thing as saying seconds to the negative 1. Okay, so really the frequency of the wave shown is 0.5 hertz. The higher the frequency, the more cycles you have happening per second. So the higher the frequency, the more cycles happening per second. So if I were to compare the following, we can see that if these two are happening in the same length of time, this has a lower frequency, and this has a higher frequency. because more wave cycles are happening in the same unit of time. On the contrary, what you'll notice is that this lower frequency wave has a much longer wavelength. It has a longer wavelength, or lambda. This has a shorter wavelength. Okay. All right. By the way, just to review how many wave cycles are happening, this has 1.5, because remember, this is 90 degrees, 180, 270, 360, 90, 180. So here we have 1.5 wave cycles. And over here we have 1, 2, 3, 4 wave cycles. 4 wave cycles. Okay. So if you wanted to figure out what is the period here, let's say these were both happening within 1 second. So the period would be 1 second. So if we were to solve for the period, 1 second over 1.5 waves. On the other hand, over here, a period would be equal to 1 second over 4 waves. Okay, so we can see the period is going to be smaller here, which means that it's going to have a higher frequency.